In the last video, we took a look at what happens if you put capacitors into combination. Now I'd like to loop back for a second and think about the act of charging a battery. Charging a capacitor, sorry. So at this exact moment, I have hooked up a battery to the capacitor, but I've caught it before any charges have started moving. So remember, what a battery does is it's going to pull electrons off of whatever's attached to the positive terminal, move them through the battery, and place them onto whatever's attached to the negative terminal. So we can kind of follow that along here and say that this battery is going to, when we pull our very first electron off, it's going to pull this electron off, take it through, it'll go through the battery and around and onto the other plate. And when we do that, we're going to create a small amount of positive charge on this plate and a small amount of negative charge on this plate, and we'll have a very weak electric field. All right, so for this very first electron, how much work did the battery have to do to move the electron? Pause and get back with me on that. Turns out I didn't have to do anything. The electric fields everywhere were zero, so it could move that very first one for free. But now, let me get ahead of myself and draw in a few more electric field lines just so we can think about this a little better. But now what's going to happen is we are going to start creating that fringe field I was talking about. And I'll draw in a couple fringe field lines. I'm also going to note here, you're just going to have to trust me on this, but I'm going to assert that when there's a wire involved, the fringe field line changes its shape to follow the wire. We'll show that quite a few videos down the road, but just trust me on that for now, that the presence of it's reasonable to know that the presence of conductors deforms electric fields, and so that's the case here. But certainly, I mean, this is a weak field because it is the fringe field, but it's there. And that means that when we move future electrons along, we're going to have to do work against this fringe field because remember, sorry, I got my fringe field, I got all my fields pointing the wrong way. Sorry about that. All my fringe fields pointing the wrong way. There, let's get our fringe fields pointing the right way. Okay, so it should be leaving the positive plate, going onto the negative plate, leaving the positive plate, going onto the negative plate, leaving the positive, going onto the negative. There we go. So remember, the electrons spontaneously want to go against electric field lines because they feel an electric force in the opposite direction. So the battery's having to do work to make the electron follow the field line. So if you remember when I said that at some point you're probably going to wish that Ben Franklin had made the other choice about plus and minus signs, here's where that's coming in to bite us. So this is our electron flow while we're charging. So let's just label that. Now, it's not taking this electron off and putting this one here. It's going to take this one off and put a different one in here. But you get the idea. There. So this can be kind of complicated to try and think about. Trying to model this fringe field sounds like that's really hard. And it is, but we can take advantage of the fact that for purposes of thinking how hard we have to work, we could imagine replacing this with a case where we've just somehow stuck the battery between the plates. We can do this because the electric force is a conservative force, so it doesn't matter what path we take, the work is the same. So somehow we've really shrunk our battery down and now it's within the plate. But again, it's going to be the same idea. So we'll say this is my positive terminal here, that's my negative terminal there. So as the battery moves my electrons, we're going to build up positive charge and negative charge. What's going to happen is the electric field is going to get ever stronger, which means that each subsequent electron that you move, you'll have to work harder. So the total work, so the potential energy stored in the capacitor is going to be equal to the the work done by the battery on the first electron plus the second electron plus the third electron. So we'll just say summing over all of our electrons. All right, so here we're going to finagle this. This sum sounds very tedious to do, and we're going to be moving zillions of charges. So we can turn this into an integral. We'll just say initial to final at the moment, of the work being done by the battery. So let's figure that out. The work done is going to be equal to the differential of work done is going to be equal to the dW bat to the differential charge I moved times the potential difference through which I moved it. But the potential difference by Q equals C delta V, I'll write it with a small q here for the moment, so we can make our limit of integration big Q for the final charge. This gives us that delta V is equal to Q over C. So we'll put that in. So this is 1 over C times dQ, Q over C dQ. All right. So then to find the potential energy stored in the capacitor, we will integrate from a charge of 0 to a charge of plus big Q. So yay, for once we don't have to change the variable there. I can pull the 1 over C out of the integral, and I'm left with integrating Q with respect to Q, which is Q squared over 2. Evaluated from 0 to Q, so we get Q squared over 2C. And by Q equals C delta V, I can also write that as 1/2 C delta V squared, and I find both forms to be equally useful. Oops, that was a horrible box. Sorry about that. Wait, what the heck? All right, let's try that again. We'll make a better box. There we go. I will also make an observation. If you remember when you looked at fluid flow, looking at when you did mechanics, we took a look at energy densities and said that they were potential energies divided by the relevant volume. So we can define the energy density of an electric field. So this is the energy stored in an electric field per unit volume. This is a lowercase u, and in physics, the lowercase sign is often the uppercase sign divided by something. So in this case, it's the potential energy. stored in the capacitor over the volume. And sorry, we can drop the delta here because obviously if you have no charge, it's 0. So I'll drop the delta. All right. So we can go ahead and pull in from our result that we just got that it is 1/2 C delta V squared. And if we do this for a parallel plate capacitor, we know that the capacitance is epsilon naught A over D. But the volume here is going to be the area of the plate over the separation there. So, yep. And the voltage is going to be ED squared, and we're going to divide this all by AD. So this is going to be 1/2 epsilon naught. We'll have A over D times E squared, D squared over AD. Cancel, 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 cancel. And we are left with the energy density is 1/2 epsilon naught E squared. And this is if we're in a vacuum. And although I only did it for the case of an ideal parallel plate capacitor, I will assert that in a much more advanced treatment, this result is true in general. Now, notice I said in a vacuum. If there's stuff in the capacitor, we're going to have to throw in a fudge factor, which we're going to get to right now. So if we put stuff in between a capacitor, the stuff you want is insulating stuff, and the fancy name for insulating stuff is dielectric material. So let's go ahead and say this is my positive plate here, and this is my negative plate here. And then what I do is I go ahead and I drop in some insulating material, dark gray. I drop in some insulating material like so. Since this is an insulator, what will happen is if we look at individual molecules and just ridiculously zooming it in, we're going to set up a polarization where this side is going to pick up a bit of where the electron cloud is going to shift a bit to the left on this side of the molecule and a bit to the right on this side of the molecule. Sometimes electrical engineers decide that they want to actually enhance that effect much more deliberately. Oops, sorry about that. And they actually choose materials that have a permanent electric dipole moment. Those are called electrolytic capacitors, and those are the capacitors that usually have the blue insulating material around them, although not always. Anyway, what if we think about what this is going to do? I've got an external electric field. I'm not going to draw the whole thing. That's being set up by the capacitor. But now within the molecule, I am running an electric field in the opposite direction, like so. And this is due to the dipole moment of the molecule. So when these combine, this has the effect of making the net field less than what it would be if there was just a vacuum between the plates. This E that I drew here. Sorry, that should be a less than sign. Now, if you're hooking a battery up to this, the battery will just keep moving charge until the voltage is equal to the battery EMF. So that means eventually you'll get up to the same electric field strength you would have had if you didn't have the insulating material here, but you would have had to move a heck of a lot more charge to do that. So the net result of this is that we characterize how much this electric field got weakened by the polarized material. We can say that our reduced field, we'll call it E prime. This will be equal to the field you would have had in a vacuum over, and then this fudge factor, which this is a lowercase Greek kappa. There are a couple different ways you can do it. If you're really good at drawing, you're supposed to be something like that. There we go. I'm not that good at it, so I kind of do this version here. But anyway, there. So anyway, in order to get the electric field up to the pre-inserted dielectric value that you'd have to move kappa times more charge to do it. So we end up saying for a parallel plate capacitor, for instance, that instead of it being epsilon naught A over D, it's now kappa epsilon naught A over D. In fact, everywhere, all you do to handle putting in a dielectric is you take your epsilon naught and you replace it with kappa epsilon naught. Some books will call that just epsilon without the naught. It's called the permittivity of the electric permittivity of the material. So revisiting our energy density here, which, like I say, we'll get to this later, but it was something I could just drop in now. If it is in a material, it's going to be equal to 1/2 kappa epsilon naught E squared. And for virtually every material, kappa is almost always a number bigger than 1, unless you're doing some really pathological things. Alrighty. So I will catch you in the next one. Have a good one.